In the previous section, I discussed the role of weather patterns and climate on forests. But climate is in itself a topic that needs further explanation, as we're currently faced with the phenomenon of climate change, really the impacts of climate on the development of forest ecosystems and the history of the Earth is really important to summarize and give some background on. The Earth's climate has always been a state of climate change. This graph is generated from data taken from ocean sediments and carbonate deposits, and pretty accurately, or with great confidence, shows the climatic fluctuations of the last 5.5 million years. And as you can see, our current climate is on the right side, and this goes back 5.5 million years. These graphs and these charts and this data can be taken back well back into the time 65 million years ago when the dinosaurs existed. And what basically has been happening, or what this shows, is that the climate is always changing across the Earth. The real question is how fast it changes and what the fluctuations are. If we look at the right side of this graph and focus in on the last 500,000 years, as shown on this illustration, what we can see are the many ice ages that have occurred over the last 500,000 years. And it's important to note that we have these peaks in warmer temperature in between. Our current climate, or what's considered stable climate period, is represented only by the short warm period on the right side of this graph. Now, anthropologically, we know that humans have existed somewhere close to 100,000 years. So really, humans, or modern humans as we consider them, have only existed across this last ice age and this last warm period. If I take the last 15,000 years represented by this little box on the right side of this graph and expand it, you can see more dramatically how our climate has transitioned from an ice age period to our current 10,000 years stable climatic period. However, it's also important to note that of this last 10,000 years, the first 8,000 years, until about 0 AD as it's often considered, was significantly warmer than it is now. This is really important when we want to track how forests developed across our landscape, because these warmer, drier periods excluded forests from much of western Montana. Now, also you notice on this graph what's known as the Roman and the medieval warm periods. If we move to another graph that better shows the development of human civilization with climate, and important to note on this is this horizontal scale is on a logarithmic scale. This means that this area known as the Holocene optimum on this graph represents 8,000 years, whereas to the right of this graph is only the last 2,000 years. What also might be noticed on here is that those first 8,000 years were significantly warmer and perhaps drier than our contemporary climate is today. This coincides with human development. As mentioned earlier, one might ask the question, if humans have existed for 100,000 years, why is it that arguably we've only been able to flourish as a society for the last 2,000 years? Anthropologists have concluded that it really was the emergence of agriculture that was allowed by a more stable climatic period that allowed societies to develop, because by farming we were able to provide with enough food that we were allowed to think about things other than just finding enough to eat. This allowed for the development of art and music and science, which has provided us with a better capacity to understand natural phenomenon. So if we look at this graph in the context of forests across the northern Rockies, we can see that really the first 8,000 years of this relatively stable climatic period was marked by warmer and drier temperatures than we have now, our current temperature shown on the right side of this graph. With moisture and temperature playing an important role in forest development, we could speculate based simply on this climatic graph that forests as we know it across the northern Rockies really didn't exist until arguably 2,000 years ago, when our climate cooled enough to allow for greater moisture to support trees. This was separated or ended with what's known as the medieval warm period. This is when the Vikings colonized Greenland and Iceland, and when northern European cultures flourished. At the same time, Middle Eastern and Mediterranean cultures were struck by famine because this rising in temperature also resulted in drought and massive crop failures on their part. This whole medieval warm period ended roughly 1,000 to 800 years ago when we went into what's known as the mini ice age. Interestingly, church records and historical records show that about 75% of the northern European population died when we transitioned from the medieval warm period into the mini ice age due to massive crop failures. This is also, however, when forests in the northern Rockies began to flourish. This can be further documented by some more recent research that has looked at pollen analysis from lake sediments across western Montana. Lake sediments are unique timekeepers because as events occur on the landscape, such as spring flowering, the pollen released by these flowers lands on lakes and is deposited with other sediment, often mineral sediment from spring snowmelt, and forms distinct layers in lake bottoms. The team at Montana State University, led by Kathy Whitlock, has examined many lake sediments across western Montana to recreate a vegetative history across the northern Rockies. This particular data set comes from Foy's Lake, which is just outside of Kalispell, and gives us a rather unique and remarkable history of vegetation across the northern Rockies. What I would like to draw your attention to is, first of all, the leftmost column that shows time since presence, starting at 0, which was a couple years ago when this work was published, all the way back to 13,000 years ago. So this lake sediment core represents a history of vegetation across the northern Rockies for the last 13,000 years. These black columns here on this graph demonstrate or represent how much pollen for particular species was found in these lake core sediments. And so what I would like to draw your attention to here is Pseudotsuga and larch. This is Douglas fir and western larch in its Latin nomenclature. And interestingly enough, the width of the black line on this graph is how much pollen was found in the lake sediment and is a proxy for how many of these trees occurred on the landscape. The wider the black column on here, the more pollen was found, and therefore it can be concluded the more of these tree species occurred across the landscape. What is remarkable from this data set is if we look at Douglas fir and larch and track its abundance down to where it really started to occur as an abundant species across the landscape, that roughly occurs 2,000 years ago. This was the start of the first cool wet period in that climatic graph that we previously looked at. What you'll also see is that this species flourished until roughly 1,000 years ago when it again declined, which is equivalent to the medieval warm period. Since the climate got warmer at that period of time, we can also make the assumption that drought was prevalent and this species that requires a certain amount of moisture died off across much of the landscape. Perhaps also this phenomenon of die-off was enhanced by fire. If we look at the very far side of this graph, we see episodic fire frequency. We also see that with the start of the medieval optimum, fires became much more prevalent across these landscapes, perhaps enhancing the decline of certain tree species. So really, when we think about the forests across the northern Rockies, this data shows us remarkable evidence that the expansiveness of the forest that we see now and the species distribution really started 2,000 years ago, which is, for tree lifespans, is a very short period of time. And that actually, after the medieval optimum, 800 years ago, is when the current forests that we see across these landscapes really developed. It was the longest cool wet period that allowed trees to grow into former grasslands. Again, this graph can show us evidence of this if we look over towards the column labeled Artemisia, which is sagebrush. We go back to the 2,000 year ago line, and we see that sagebrush played a much bigger role across western Montana until 2,000 years ago, where it started to become limited by increased moisture, which allowed tree species to dominate the landscape. The same can be said for the column Poaceae, which are grasses. You can see again, if you go back to 2,000 years ago, grasses and grass pollen was much more abundant across this landscape than 2,000 years ago when it got wetter, and then again became much more abundant at the time of the medieval optimum. So if we look at a temperature graph of the last 2,000 years, reconstructed from tree cores, the width of the growth rings on the cores indicating when conditions were wet enough for ample growth to occur because tree growth was not limited by drought. This graph was created from multiple data sets from across the northern hemisphere. So this includes northern Europe, North America, Siberia, areas where trees were found that were not influenced by neighboring trees but more influenced by climate and higher elevations. There are a couple of things that can be seen from this. First of all, the medieval warm period is that peak in the middle, followed by the mini ice age. But the other thing that this graph really shows is, since it's from different data sets, it shows the tremendous variability in climate that occurs across the northern hemisphere, and that isn't adequately portrayed by graphs that only show averages. So even though it may have been cold in North America 13 AD, it may have been warm in a different part of the northern hemisphere. So climate is a highly variable phenomenon that occurs across our northern hemisphere, and it really can't be defined by a single line that shows an average temperature. On the right side of the graph, the black line is speculated climate change, global warming caused by, or speculated to be caused by human activities, including carbon dioxide emissions. So we can see that we are potentially in a period of time when warming of the air temperature is going to be a phenomenon that affects our landscapes and our forests. To further show the tremendous variability in climate and weather, this graph is only of the last 100 years of the dominant climatic influence on the northwestern United States, known as the Pacific Decadal Oscillation. These are the temperatures and the weather patterns that come off of the North Pacific that influence how much rainfall we get and what the temperatures are like. This graph represents annual averages, both summer and winter temperatures, starting in 1900. And so what's evident on this graph is that the black line, which is the average, does not adequately represent the maximums and the minimums of temperatures. And this is very important because maximum and minimum temperatures are the factors that determine a plant species distribution and growth rate. So where a tree grows is not necessarily determined by the average temperature, but by the maximum cold and the maximum heat that site may actually experience during a time. What's also shown here is that from 1940 until 1980, we experienced a prolonged cool wet period surrounded by hotter dry periods across the northern Rockies. So we have these tremendous climatic fluctuations that occur at micro scales and at macro scales. So across thousands of years, the trends, and across tens of years or single years, this graph helps show us that climatic variability is really a normal feature of northern Rockies and northwest ecosystems. These following depictions kind of demonstrate what we've learned about climate and weather patterns over the last 20 years, where we've made tremendous advances. We've learned that it's really oceanic bodies that dictate weather patterns and climate across continental masses. Here, Pacific Decadal Oscillation is really the northern Pacific surface temperatures. What's known as El Nino or Southern Oscillation is equatorial waters on the Pacific, but we're also influenced by Atlantic multidecadal oscillation and Arctic oscillation. So it's really the large water bodies that largely determine how climate and weather patterns occur. Here, just a closer depiction of ocean temperatures and how ocean surface temperatures will vary across wide expanses, and how these ocean temperatures in turn influence climatic patterns. When we experience a warm phase across the northwestern United States from Pacific Decadal Oscillation, actually the North Pacific is cold, which creates a low pressure circulating counterclockwise, which draws warm air from California up across Montana. Quite the opposite, when we experience a cool phase, northern Pacific Ocean temperatures are warm, which support a high pressure system which circulates clockwise, and that clockwise circulation draws cold air down across Montana from Canada. If we look at Pacific Decadal Oscillation and its influence on our forests, here's a graph that shows the last 450 years of climatic variability across the northwestern United States. Above the line 0 is the warm phase, below the line is the cool phase. Now remember, these represent average temperatures, not annual extremes. But even these average temperatures can tell us a lot. From 1945 approximately until the late 1970s is one of the longest cool wet stretches in the Pacific Decadal Oscillation of the last 450 years. And with a long cool wet stretch comes more moisture, which would have had profound effects on our forests as well. Now, when a separate data set that looked at extreme fire years is superimposed upon this, represented by these years. The years 1802 all the way through 2003 were determined to be extreme fire years based on fire scars occurring on trees across the entire northwestern United States. So in other words, in 1802, forests in Montana burned, forests in Idaho burned, forests in Oregon burned, forests in Washington burned, indicating to us that it was a really bad fire year. You will notice that 2000, 2001, 2002, 2003 are on this data set because those were also years when much of the Northwest supported large landscape level wildfires. If we superimpose these years onto our climatic graph, we can see that climate has a profound effect on fire, that when we have a hot, dry summer, or actually a series of hot, dry years, we tend to have larger landscape level fire events. And this makes perfect sense because it typically takes a landscape several years to dry out. So several years of drought will create larger wildfire events across the landscape or enable larger wildfire events. You'll also notice that when we have cool, wet periods, we do not have these landscape level fire histories. This is particularly important if we look at the last century of the role that fire and human interactions occurred across the northern Rockies. For example, if we look at historic photos, this one taken in 1888 by W.H. Culver of the east side of the Judith Mountains being located in central Montana. If you look at the mountainside behind these horses and use the rocks in the front as a place reference, those mountains are largely grass covered with some trees on them. If we take that same picture again, 100 years later in 1980, we can see that the forest has vastly expanded across this mountain range, and where it used to be a rangeland with some trees, it's now a forest with some grass. Why this occurred and how this occurred has been the subject of much debate, but largely since we know that moisture gradients are really what drive forest species distributions, whether a tree can grow one place or another, we can pretty well conclude that it was increased moisture and perhaps lack of fire that allowed these forests to expand their ranges. This same phenomenon of forest expansion has been documented in other regions of northwestern United States. These maps, created by Paul Hesburgh's research group out of Wenatchee, Washington, basically looked at large landscapes, roughly 10 to 30,000 acres on the lower Grand Ronde in eastern Oregon and Washington, where this map on the left indicates the green is ponderosa pine forest and the yellow is grassland in the 1930s. By the 1990s, you can see that the ponderosa pine forest has vastly expanded its range across this landscape. Similarly, if we look at wetter forested landscapes, where grand fir is a dominant species, on this left graph of this drainage in 1930, we can see that the light green is ponderosa pine cover, the blue-gray is Douglas fir, and the bright blue is grand fir. The beige color is herbland or grassland on this. So in the 1930s, this was a highly fragmented, complex landscape of different species and different cover types. By 1990, what you can see on this is that grand fir and Douglas fir have dominated this landscape with very little grassland left, very little ponderosa pine cover. If we consider climatic influences, particularly that long, cool, wet period determined by the Pacific Decadal Oscillation from the 1940s to the 1980s, that increase in moisture certainly enhanced tree regeneration and tree growth. In addition, the role of human fire suppression, grazing that reduced the competition from grasses for trees probably also enhanced this process. Any landscape across the northern Rockies that's covered in forest has a certain history of past disturbance and growth rates on it. If we look at this mountainside and define the different tree species, their ages, and their distribution, we can reconstruct the past history of disturbance on this. In the center, in the black circle, we have a remnant stand of old larch trees that survived a massive wildfire. These larches are 200 plus years old, and being the most fire-resistant, survived fires. What came in around it is a dense lodgepole pine stand that's only 80 years old. In the drainage bottom, where it's cooler and wetter, grand fir managed to survive that fire and thus did not burn in the past fire. And to the left side of this picture, on the northeast side of the mountain, again, cooler temperatures and more moisture allowed Douglas fir and larch and grand fir to establish. This mosaic of tree species and age classes is what defines forests of the Northern Rockies and is determined both by topography and climatic influences and the role that those climatic influences have on disturbance processes such as wildfire. Any landscape we look at can be deconstructed to show the history. In this particular case, this is part of the 1910 burn where a vast portion of northwest Montana burned. Here the surviving trees are the old ponderosa pine trees that can be seen on this mountainside and that have since been crowded by the prolific regeneration of Douglas fir on this landscape. So if we went here in 1920, this would have been a barren hillside with grasses and forbs with only a few ponderosa pine trees on it. It is now covered with dense Douglas fir. Any landscape will show these patterns of past disturbance histories and the influence of climate, aspect, and topography. Even the drier forest types in central Montana show this phenomenon where in the background, in mid-slope of this north-facing aspect, Douglas fir stand, shown here by the older trees that are starting to die out, and that the impacts of both grazing and a wetter climate allowed for Douglas fir to expand into the historic rangeland in front of it, shown by the younger, denser, smaller trees in the foreground.